Most of you will know Dr. Kathryn Hadler, an internationally renowned scientist in mineral processing and beneficiation, recently appointed the director of the European Space Resources Innovation Centre, ESRIC, based in Luxembourg, and she's now going to guide us around the moon. And as Andy Weir explained in his Artemis book, there seems to be an incredible amount of oxygen on the moon, but we need a lot of energy to get it. So Kathryn Hadler will introduce us to a number of different techniques to extract oxygen from in-situ resources. Kathryn.
Thank you very much. I appreciate that I stand between you and lunch, so we will I will keep an eye on the time. So, as Lisa said, I'm the director of the European Space Resources Innovation Centre. We've talked around resources a lot this morning. We haven't talked explicitly about resources, about where they come from, where they might come from in the future, and how we resource space exploration, and that's exactly what I will do. So we will address some of the comments made by the students. In the earlier video, we will talk about what Geraldine mentioned earlier about space and commercialization of space, being able to save the planet. And we will also touch on concepts that Ed mentioned about blind progress and circular economy. So, ambitious, but we at ESRIC are nothing if not ambitious. So let me start with this image. Now, this image, I love this image. What the space sector does brilliantly, and the space resources sector does brilliantly, is visualize what the future might look like. And this is an ESA image, and this, I think, illustrates it very nicely indeed. You can see at the bottom, down near the rover, there are some people for scale, and we always need people for scale. And this shows the extraction of propellant and what a future lunar architecture might look like. We'll come back to this image slightly later. But what's important about this is that space resources mean different things to different people. So we saw from the student videos earlier on this morning, when we think about space resources, some people think about asteroid mining, bringing back resources from asteroids for Earth so that we can avoid the need for mining on Earth. For some people, it's about space tourism, this future of space. There's opportunities in terms of a new space economy, in terms of in-space manufacturing, on-orbit refueling. But what's clear is that in order to move forward in space, we need to remove this need that we currently have to take everything with us. So, as Ed mentioned earlier on this morning, Ellen MacArthur realized in the ocean that she had to rely on everything she had with her. Currently, we need to take everything for any space mission with us. If we can produce usable resources in situ, then this transforms this need to take resources with us. And that's exactly what in situ resource utilization is about. We call it ISRU, or space resource utilization. So going into space to extract and produce usable resources from the things we find around us. And as Peter mentioned in his talk, this must be based from the beginning, from first principles, on concepts of circular economy. So let's see the importance of ISRU. That's certainly not my slide. There we go. So the importance of space resources, or ISRU, it forms a critical part of space exploration strategy. So in the second set of videos, one of the students says, oh, it seems like science fiction. This isn't science fiction. This will happen. It is a critical part of space exploration strategy, as you can see from this slightly busy diagram. And this is from the ISRIC, the International Group of Space Agencies. It's the agreed roadmap, if you like, for space exploration. And we can see that space resources forms that critical part. In the near term, in the next few years, we'll see demonstrations of the production of usable resources on the moon. And by usable resources, here we're talking about oxygen or water. So things we can use for propellant or for sustaining life at the demonstration scale. And then we move into pilot plant type demonstration. So here we're thinking about hundreds of kilos. This is a significant scale of operation. And for that, we will need the systems to be either continuous or in some kind of reliable situation. And then the long-term vision is that then we can produce continuous, reliable resources of some kind of meaningful scale, 50 tons or so a year. That, from nothing, is a significant challenge. And it is complex. We talked about systems, or Peter talked about systems in the talk previous a lot. These systems are complex. It is not just about going and producing a bubble of oxygen from the lunar soil. It's about designing an entire system based around space resources. So we've got, on the right-hand side, you can see consumables production. Here we have oxygen and water on the surface of the moon. We also need to store that oxygen. We'll need some kind of construction and manufacturing in place. We need infrastructure. We need to be able to build things. And then if we also need to provide habitation, life support, if there are astronauts to support. This is fundamentally based on the properties of the resources that we find in situ. So ultimately, this is about resources. It's about resource extraction and resource use in a hostile, resource-scarce, and pristine environment, and that is critical. So although it will both enable and produce scientific discovery and economic activity, we must remember that it's about resource-scarce, hostile, and pristine environments. And to do this, to tackle this challenge, it cannot be done by one space agency, one company, but will require an entire community effort, and that's what we see very much in the space resources community. Now, I'm just going to spend a couple of slides just talking about one specific example, and that's the example of oxygen. One of the students in the first batch of videos this morning mentioned, well, you know, if people are going to go out into space, where's the oxygen that they can breathe? Actually, there's plenty of oxygen on the surface of the moon. It's bound up into the minerals in the lunar regolith. So to extract that oxygen, we can extract it from the lunar regolith using a number of different techniques. So we can use chemical reduction, we can use electrolysis. We can use molten salt electrolysis, that's the FFC process there, molten regolith electrolysis. There's a number of different processes. There's a lot of research that has been done and that is being done on looking at processes to chemically extract oxygen. But we also need to excavate that lunar regolith. So we need some kind of digger system, some excavator. And then there's a step in the middle. And this step in the middle is beneficiation. Now, this, I think, is a huge challenge, which I would say, because this is my field of expertise on Earth. I come from the terrestrial mining sector. So this beneficiation step is the physical separation, handling of the regolith before it goes into the reactor. Now, you'll see from this diagram that in both the beneficiation and the extraction stages of this simplified flow sheet, very, very much simplified, there is waste produced. And this is drawn very much in a linear fashion. And we know that we should be thinking in terms of circular economy. So actually, what we should be doing then is identifying what the uses of those waste streams are from the very beginning. And in a resource-scarce environment, we will absolutely have to do that. So I can use the waste from the extraction, perhaps, as a feedstock for some kind of manufacturing process. I can use it in construction. But the reason that this diagram is drawn like this is because this is pretty much the simplified metal production flow sheet on Earth. So the way in which we extract metals on Earth is by the same process. We excavate, we do some kind of beneficiation, and then we do some extraction. And on Earth, we don't do this in a circular way. We produce huge amounts of waste, as we will see. But on the moon, we can see that we have these linked stages in our oxygen extraction process. They are linked so that the feedstock required by that final stage, that extraction stage, actually defines the requirements of the whole process. And forgive me just for this graph for a second. I just want to show the importance of thinking through the entire system, as Peter introduced so beautifully. In this is a theoretical study And all we're looking at is what happens if you strip out components of the regolith and what that does to your mining scale and what it does to the size of a reactor, theoretically. The reason for this is to say, do I want a big reactor and a small mine, or a small reactor and a big mine? And these are really critical questions, and these are critical questions that we don't know the answer to yet. And the reason this is important is because this has a huge implication on the design of our systems, on the technologies, on the way in which we operate, on the amount of waste that's produced, on what we do with that waste. If I have a use for the waste from the outset, then I can design my process with that in mind. So we need to approach this very much in terms of the system rather than individual processes. And it's important to note also that all of these systems have to be completely reliable in a hostile environment, and that's something that we don't do now. Currently, terrestrial mines, when things break, there's somebody there to fix it. This is not the case in space. So we have to solve a huge number of problems and design a huge number of technologies to progress this concept. So there's a large opportunity for development. But let's return back, because at the very beginning, this talk is called Space Resources for the Benefit of All. Now, when we talk about ISRU, or space resources, then really we're talking about not all. We're talking about a few people, maybe a few astronauts, maybe the development into the long-term future. So how do we link this to the benefit of everyone? And just take a look again at our lunar operation. So this is our ESA diagram, and you can see I've highlighted some things of interest. So we've got resource extraction there. We've got infrastructure, that's the landing pads, one critical piece of infrastructure that's required. We've got transportation, there's some habitation, energy, storage, and processing. So some important features there. Let's take a look at a copper mine. So this is a copper mine high up in the Andes, and this is one of it's called my holiday pictures. But I spent a long time doing research into mining and traveling around and working on various mines. So this is a copper mine very high up in the Andes. We produce, just for scale, we produce about 20 million tons of copper per year. That need is increasing with the energy transition. So as we move through the energy transition, we need 4 times as much copper, for example, for an electric vehicle compared to an internal combustion energy car. This mine, this image, it's not an easy image to look at. The scale of damage is huge, but at the same time, one can't help but be impressed by the amount, by what humans can achieve in terms of engineering. I mean, this is a huge mine. For scale, some of those trucks that you can see, the arrow to infrastructure, that's a 250-ton truck. So those trucks are huge, the mine is huge. But we see the same features as in our lunar mine. We've got resource extraction, transportation, infrastructure. There's some energy infrastructure on the top of what used to be a mountain up there. We don't really like to think about where our resources on Earth come from, but we will happily use the products of resources. But anyway, to continue on our tour around this mine, we've got a waste pile highlighted there and a stockpile. The waste pile's all the material I've had to mine to get at the ore which I want in the first place. The stockpile's ready to go into processing, and there we have on the right-hand side the processing facility. This is where the beneficiation happens. And then the waste. So we've got a waste pile on the left. On the right-hand side, this is tailings or waste. We use, in the terrestrial mining sector, enormous quantities of water to separate minerals. It's the most effective way of doing it. And so we produce these huge amounts of what's called tailings or waste. So we can already see some opportunities where perhaps rethinking this process, some concepts from space resources might come in useful in the terrestrial sector. Just by way of diversion here, to give an idea for scale, because we often talk about the moon and carrying out operations on the moon without really a sense of scale. So this diagram is one I made for one of my classes, and I quite like it just to give a sense of of the scale of the moon. So on the left, we have Shackleton Crater right at the lunar South Pole. And on the right-hand side, we have one of the large copper mines in the US, Bingham Canyon. It's one of the largest holes in the ground. Not the largest, but one of the largest. And we can see that the Shackleton Crater is 21 kilometers in diameter, Bingham Canyon 4 kilometers wide. Again, these trucks here are 200, on the right-hand side, are 250-ton capacity trucks. So it does give us a sense of scale of the moon. Now, we're not going necessarily down to the bottom of Shackleton Crater because it's very steep, it's very inaccessible. But it's always interesting just to take a step back and think about this. But anyway, now let's return back to this concept of resources in space and resources on Earth. The challenges that we have on Earth is that mining is water and energy intensive. It uses huge amounts of water. It uses huge amounts of energy in crushing rocks. Its efficiency is relatively low. And nobody likes talking about mining. We really don't like to talk about mining, to think about where our resources, our metals come from. And I know this coming from that sector. There's a significant environmental legacy that we must now address for the future. On the other hand, we have space resources, and on the moon, we've got a number of different environmental challenges. We've got vacuum and low gravity. The dust is everywhere. The dust will be a real challenge to work with. There's no process fluids whatsoever. We cannot design systems that will work with freely available water. So this forces us to think differently, and it doesn't yet exist. And so for that, we now have an opportunity. And we have an opportunity to start this resource use case from the very beginning. And we can do this by rethinking how we go about using our resources and how we build our systems around resources. And so in that respect, space resources must be used as an example of how to do this well. So just for the few minutes, bear with me for 5 minutes longer, and we'll just talk a little bit about ESRIC, because those challenges that I've presented to you, the challenges and the opportunities, this is exactly what we are doing at ESRIC. So ESRIC, the European Space Resources Innovation Centre, is relatively new. It was formed in 2020 as a relationship between, as a result of a kind of agreement between the Luxembourg Space Agency, and Luxembourg is at the forefront of space resources. It really is a huge amount of activity in space resources in mighty Luxembourg. My new home, I've recently relocated there. It's absolutely beautiful. And the Luxembourg Institute of Science and Technology, and ESA joined later in 2020 as a strategic partner. ESRIC is there to be a home for space resources in Europe. So both in terms of science and technology, so we are doing research, but also to support economy in this new and fast-moving area. We have 4 areas in which we're active. So research, business, knowledge, and community. I'm just going to touch very quickly on a couple of these. One of the activities that ESRIC does in partnership with ESA and with the LSA is organize Space Resources Week. So what I would do is recommend that you come and join the party in Luxembourg. It'll be next year, we're looking at finalizing the dates. It's spring, it will be April, May 23 will be the next edition of Space Resources Week. It is the largest gathering worldwide dedicated to space resources. So this year we had 350 people in person and 650 people online. It was free to register. I think that's really important in terms of accessibility. And we cover all topics related to space resources, including legal and economic aspects. So that's one of the activities that ESRIC has in terms of really bringing together. There's huge pockets of activity. There's lots of startups, lots of energy and enthusiasm around space resources. And what ESRIC is there to do is really form that focal point in Europe. One of the other really innovative things that's happening at ESRIC is the Startup Support Program, again in partnership with ESA and with Technoport, which is a business incubator in Luxembourg. And here we are really providing the world's first and only business incubator purely focused on space resources. Donatella mentioned in the panel discussion earlier about the long lead time and this being too risky for investors. And the objective here is to provide the opportunity for those space resources startups with a really good idea to de-risk and grow their business. It's completely open to anyone from around the world with a good idea and a startup and that qualifies as a startup. And there's five startups go through into a 3-month pre-incubation phase, of which one then moves forward into a full 2-year incubation with 200,000 euros to develop their business. We currently have just finished the first phase, and the next call is now open. So if you are a startup and you have an idea, then take a look at the website. We're not just supporting community and business, but also carrying out research and building research capability. And again, if we go back to this diagram, we're looking at individual technologies, so we have research activities in individual technologies, but also the bigger picture. How do we develop these integrated systems? How can we look at the building concepts of circularity in terms of recycling and so on? So this is an example, a snapshot of some of the projects that we have active at the moment, and you can see that they're focused on producing oxygen on the lunar surface, which is in line with ESA strategy, but also what we do with the byproducts, what we do with the metals. What do we need for infrastructure? And there are companies that are interested, are partnering with us, such as Airbus, Air Liquide. We also work with a Luxembourg-based startup, Mana Electric. And their business is based on building solar panels from space materials. In addition to that, we've got a sizable grant from the Luxembourg Funding Agency to build a whole new research group that will focus on things like legacy, environmental legacy, life cycle assessment translated to space resources. Space resources is fundamentally, as I said at the beginning, it's about resources. It's about resources that will enable us to explore, sustain our time, our presence in space, that will enable us to travel onwards to Mars, that will enable us to generate this new in-space economy. But it's about starting from the beginning with the right intentions. So starting with this concept of being in a hostile and pristine environment. And in that respect, we have a real opportunity to avoid the problems that we have, the legacy that we've left on Earth, and by using space resources to demonstrate how this can be done in a responsible way. And at the same time, the technologies that we develop for those hostile, pristine environments have genuine application for what we do on Earth. And we can use those to transform the way in which we extract and use resources on Earth. So with that, let's see. Thank you very much.